The objective of irrigation planning is to ensure that the type of irrigation system installed will meet the needs of the operator, fit the requirements of the soil and proposed crops, and provide irrigation water management on the land. To achieve this objective, several factors must be considered during irrigation planning. Soils. The soil is one of the most important factors to consider in irrigation planning. It must be capable of sustaining yields large enough to pay for the installation and operation of an irrigation system in addition to normal farming costs, and it must do this without significant deterioration over long periods of time. A soil map is essential. It is the basis for determining whether the soils are irrigable and is used by the planner to match the irrigation system with the soil. If the planner has only a standard dryland soil survey and determines that the information is not detailed enough to use in making necessary decisions, a supplemental irrigation soil survey should be used. Adequate soils information enables irrigation planners to make decisions based on important soil properties such as intake rate, water holding capacity, permeability, depth, slope, erosion hazard, water table location, drainage requirement, and salinity hazard. The use of these properties as specific planning and design criteria and to determine irrigation limitations is discussed in detail in individual state irrigation guides. Topography. Topographic information is essential for planning an irrigation system. As a minimum, surveys should include enough detail to show the source and elevation of the water supply for the area to be irrigated. Landscape features such as fences, buildings, roads, and shelter belts that may affect the design of the system, present field boundaries and direction of irrigation, location and capacity of permanent irrigation ditches, pipelines, and structures, location and capacity of temporary field ditches or portable pipes and flumes, and the drainage pattern of the farm, including the location and capacity of ditches for wastewater disposal and other drainage structures. The scale and contour intervals of topographic maps needed will vary, depending on site conditions and the methods of irrigation under consideration. The scale may range from 1 centimeter equaling 10 meters, or the English equivalent 1 inch equaling 100 feet, to 1 centimeter equaling 50 meters, or the English equivalent of 1 inch equaling 200 feet, depending on the irregularity of the ground surfaces and the concentration of obstructive landscape features. Likewise, the contour interval may range from 0.1 to 3.0 meters, or the English equivalent of 0.5 to 10 feet, depending on the slope. The objective should be to provide a map containing all the necessary data at a scale large enough to display the irrigation plan without crowding. A complete grid survey usually is needed if land leveling is required. Grid or contour maps are not always required for planning irrigation improvements. For example, in the partial reorganization of an existing system, the planning of grade control structures in a properly located ditch may only require a profile and cross-section of the ditch with the turnout locations and elevations to field laterals noted. Likewise, the installation of a sprinkle system does not require the same detail of topographic information that is required for a surface irrigation system. Water supply. Compliance with state laws in obtaining water rights and in using irrigation water is the responsibility of the land user. However, NRCS should advise the farmer about any water laws that may affect the plan or installation, and encourage the farmer to see a lawyer for interpretation of a law or for advice on a legal problem. The quantity of water available for irrigation, the rate at which it can be delivered to the farm or fields, and the reliability of the supply must be determined. The rate at which the water can be delivered to the farm usually is expressed in cubic meters per second, in miners inches at the head gate or diversion, or in liters per second if from a pump. When irrigation water is transpired by plants, most of the salts that were in the water remain in the root zone unless there is enough rainfall or excess water provided in the next irrigation to leach the salts downward. In areas where water quality is not known, tests should be made and evaluated by soil scientists or other specialists. The total concentration of soluble salts, the relative proportion of sodium to other cations, the presence of toxic amounts of boron or other elements, and the relative concentration of bicarbonates to calcium and magnesium should be determined. Facilities to test water quality are available through state agricultural colleges, public health departments, and commercial laboratories. Erosion control and drainage. The irrigation planner is faced with simultaneously meeting the following three objectives. 1. Apply water efficiently without causing erosion. 2. Protect against erosion caused by rainfall. And 3. Provide required surface and subsurface drainage. The physical layout requirements for proper irrigation are often directly opposed to the physical requirements for protecting the land against erosion by rainfall. This is especially true with surface methods of irrigation. To protect a field against erosion caused by storms, it is often desirable to lay out the rows so furrows are nearly level. However, for water application, it may be easier to install a less efficient system by running the rows directly downslope. Using contour irrigation with or without terraces and contour bench leveling to modify slope often satisfy both requirements. In other instances, conventional erosion control practices are installed and the irrigation water is applied by sprinklers. Similarly, the needs for drainage and irrigation are not necessarily compatible. On some soils, it may be desirable to apply irrigation water by ponding, such as by the use of level borders, but such a practice may not be compatible with the drainage requirement for removal of excess stormwater. On the other hand, land leveling for irrigation usually helps the surface drainage of a field by eliminating small ponded areas. The application of irrigation water may change the balance between recharge and discharge of the groundwater, which may result in changes in the elevation of the water table. Usually, when water is diverted from an outside source for application to an area, the water table rises and may reach a point where subsurface drainage is required. When irrigation water is pumped from the water table may drop. If sub-irrigation is the method used, subsurface drainage must necessarily be of a controlled type. When the planner has met the requirements for efficient irrigation, effective erosion control, and adequate surface and subsurface drainage, he or she has developed a plan that sets the framework for conservation irrigation by the farmer.